So we talked about describing a relationship between two numeric variables. Now, if you think back to just describing a distribution for one numeric variable, what would you use? What are the aspects of a numeric distribution that you'd want to describe? I'm sorry?
Can you repeat that?
If you had a single numeric variable, or numeric distribution, or a numeric data set, and I asked you to describe it, so you draw a histogram or a box plot or something, what are the things that you would use to describe? Range. Okay, so range is a measure of spread, right? Okay, so one thing we want to talk about is spread. What else do we want to talk about?
Median, or the mean.
Okay, the center and the shape. The shape, center, and spread. Okay? Now, to describe the center, we have numbers. We have the median and the mean. Those are numbers that we can calculate to describe the center. To describe the spread, we also have numbers. Okay, and what numbers can we use to describe the spread?
Yeah.
The standard deviation. I'm sorry? The interquartile range, the IQR. What else? And the range, okay? Z-scores don't describe a distribution, they describe individual points in relationship to everyone else, okay? So we have numbers to describe the spread, we have numbers to describe the center, okay? Same concept applies when we're describing a relationship, okay? But we have one number, and it's going to describe both the strength and the direction, okay? So we have a numeric summary. Describes the direction and strength of a relationship. And that number is called correlation. So the correlation. So the correlation is just a number that we use to describe the strength and the direction of a relationship. Okay. Correlation. And the symbol for correlation is R. Okay. What's the symbol for the mean? X bar. Okay. The symbol for standard deviation? S. Okay, S or SD, that's fine. And the symbol for correlation is R. Okay. Now, calculating the correlation is really tedious. Okay. And I'm not going to teach you guys how to calculate the correlation by hand. Okay. We're just going to say there is a process. If we wanted to learn it, we could. Just like the standard deviation, if we wanted to, we learned how to calculate the standard deviation by hand. Okay. The correlation, there is a way to calculate it by hand, but it's rather tedious. I'm not going to make you guys learn it. Okay. So we will not learn how to calculate this by hand, but we will learn what it means and how to use it. Okay. So we generally, we use a computer, okay? Excel can calculate correlation for you, or any other computer program that's designed to handle data can calculate it, okay? So we use computers to calculate it. Or I will calculate it and tell you. here's some rules about R though, okay, about correlation. R has to be in between 0 and 1 inclusive, okay? Is this notation okay? Is this?
Yeah. Yes.
You guys understand? This means R has to be in between 0 and 1, okay, including 0 and 1. I'm sorry, it's not 0 and 1. R has to be in between 1 and -1. I apologize, I'm confusing myself. R has to be in between -1 and 1 inclusive. Sorry.
Oh.
Yes.
I'm sorry, what does it say right there? We will not what?
Learn how to
Oh,
calculate R by hand. Learn. Alright, so if R is positive, the relationship is positive. And if R is negative, the relationship is negative. So the sign of R is the sign of the relationship. So positive R If R is close to 0, the relationship is weak. And if R is far from 0, so what does it mean for R to be far from 0? Okay. Closer to 1 or -1, okay? So being far from 0 means R is close to 1 or -1. So if we see R is -1, what does that mean? Strong negative relationship, okay? Or perfectly strong negative relationship. So example, a relationship that looks like this would have R equal to -1, okay? Because here, the dots are exactly on the line, meaning if I know one variable, how good are my predictions about the other variable? Yeah, they're perfect, okay? Because they're perfectly on that line. So if I know the equation of the line, I can make perfect predictions about the other variable, okay? And it being negative, what does that mean? Negative relationship. So larger values of one variable correspond to smaller values of the other variable. Okay? Something like this. What do we have?
R equals 0.
Yeah, do we have any kind of relationship? No, no relationship. So here, R would equal 0. Okay? It's not a positive relationship nor a negative relationship. There really is no relationship. We've got R equals 0. Okay. So R tells us the direction and the strength. What does it not tell us? The shape, okay? It doesn't tell us the shape. So we have to keep this in mind. All right. How can we figure out the shape of a relationship? So R does not tell us the shape. Okay. To find the shape, we have to make a scatter plot. Okay? There's no way around it. Scatter plot and decide whether it's linear or not. So we have to make the scatter plot and decide if it's linear or not, and then we can use R. Okay. Now technically we could calculate R for any two numeric variables. Okay, we got two numeric variables in a that we can calculate R for it. However, it is only meaningful if the relationship is linear. Okay. So we can it's like I can report the weight of any object to you, okay? But the weight really only has meaning if you're worried about lifting it or, you know, placing it somewhere, something like that, right? You go to the store and you're going to buy a sofa, okay? They can tell you the weight of any sofa in the store, but you really only care if you're going to bother moving it or lifting it or something, right? It's just going to stay put. You don't really care if the sofa is light or heavy. Likewise, we can calculate R for any set of numeric variables, but it's only meaningful if there's a numeric relationship, okay? So what I want you to do is, part of your reading, you're going to have to read the chapter, okay? But pay very careful attention to pages 139 and 140, okay? So those are, and they talk about, you know, the different values of R, and they show several examples there. Okay, and then it goes into the calculation of R, but again, we're not going to learn R by hand there. Okay, is that okay? Coverage of R. So now we are going to the application of this is now we can model a linear trend with a regression line. Okay. this is the idea where, you know, we have a scatter plot, we've got some dots. And we want to fit a line that summarizes our data. So here is, this data is taken from, this is our example in the book, and it basically said they went to a library and they looked at a whole bunch of different books. And they looked at the book and they went and they said, how many pages are in this book? Oh, there's, whatever, 700 something pages, okay? So they counted how many pages are in a book, okay? And they also, so some books are fat and some books are thin, and they also took the book and they measured how wide or how thick the book was, okay? So they measured how wide this is. So this is like, you know, 1.1 inches or something, okay? And they did that with a whole bunch of different books, all right? And what do you think the relationship looked like? It looked something like this, okay? And what they found is that in general, books with more pages were thicker than books with fewer pages, okay? So this is the width or thickness. And then they wanted to come up with some kind of equation to summarize this relationship. So if we want to make a straight line equation, what does a straight line equation look like? What's the equation of a straight line? Yeah, so in algebra, you learned, we learned that the equation of a straight line is y equals mx plus b. Is that right?
Yeah.
Okay. Now what is m? M is the slope. And what is b? The slope. And b is the intercept. Okay? And what is y? It's the value that you're trying to calculate. Okay? And what's x? X is the value you plug in. Okay? So you plug in x and then you get y. This is your equation of a straight line. Okay? In statistics, for whatever reason, we change up the letters on you. Okay? Alright, so in statistics, well, it's not whatever reason, okay? In statistics, it's not y, but it's y hat, okay? There's a little little roof over y, and it's we call it y hat. Okay, and this is equal, and here the intercept comes over here, and we use the letter a. Okay, plus, and the slope comes over here, and we call it b x. So here the slope is b, and the intercept is a, and the value we're trying to calculate is y hat. That's okay, right? Yeah. So we just change the symbols on you a little bit. Okay, so y hat, the reason why we use the hat is because anytime you see a hat, it means it is our prediction. Okay, so y hat means this is our prediction for y. Okay. Our prediction for y. Alright, and that makes sense because we're making a regression line, a line where we're trying to make predictions for the other, right? So when we talk about the strength of a relationship, we said knowing one variable either allows us to make good predictions or bad predictions, okay? So knowing the number of pages in a book, if we have a strong relationship, will allow us to make a good prediction or fairly good prediction of how thick the book is going to be, okay? So if somebody tells me, oh, I've got this book, it's got 300 pages in it, I could say, well, based on what you've told me, I estimate that the thickness of the book is such and such number. Is the book necessarily that number? No. The book could be thicker than that. The book could be thinner than that, right? But based on the number of pages in the book, I can make a prediction. And so that prediction is going to be y hat, okay? The value y, which we don't see in the equation, is the actual value that it takes, okay? So the difference between y and y hat, so y is the actual value of our data point, and y hat is our prediction. So so let's say there's a book with 300 pages. Okay? My x here is the number of pages. We're using the number of pages to make a prediction for the thickness of the book, right? So x is the number of pages. I use the pages, the number of pages, to predict the thickness of the book, which is y. So here I have x equal to 300. So let's say I plug this into some equation, and the y that it spits out. So when I plug, so let's say I have an equation and I plug it in, and let's say the value it spits out is 0.63. Okay, 0.63 inches. Is that my y or is that my y hat?
Y hat.
That's my y hat, because I put it into the equation, and the equation gives me y hat. Okay, so if I plug this into my equation, it spits out 0.63 inches. Okay. So 0.63 inches is my y hat. Okay. This says, knowing that the book is 300 pages long, I predict that the book is 0.63 inches thick. This is my prediction. And basically my line of reasoning is, if I know the book has 300 pages, I predict that it is 0.63 inches thick. Okay. And that's so y hat is equal to 0.63. Let's say we go and we take a ruler and we actually measure how thick the book is. How thick is this book? It doesn't matter, okay? I mean, it could be anything. We don't know. We go and we take a ruler. So we measure the book with a ruler. Okay, and the book is 0.70 inches. Alright. So y, the actual data point, y is equal to 0.70. So the difference between the actual and what we predicted, this is known as the residual. Y hat, okay. The residual sometimes we also call E. Okay. This is the actual data point minus the predicted value. So here my residual is equal to 0.70 minus 0.63, 0.07. And what does that mean?
That we predicted less than it was.
Yeah, it means the book was 0.07 inches bigger or thicker than what I predicted. Okay? Can my residual ever be negative?
Yeah.
Yeah. And what does it mean to have a negative residual? It means the actual point was smaller than what I predicted. Okay? Means the actual value was greater than my predicted value. Okay? A negative residual, just the opposite. Okay, so how do we get this regression line? So the regression line, once again, is y hat is equal to a plus bx. Okay. What is b? B is the slope, and a is my intercept. Well, the regression line, what the mathematicians figured out was that the best line to summarize data, okay, is going to be the line that minimizes the squares of the residuals. Okay, so you could pick any line and you could calculate the difference between the actual points and what we predicted. Okay, and that would be your residual, right? And if we found the residual for every single data point, and we squared them all and added them up, that's going to give us the sum of squares residuals. We don't need to worry about that, okay? But the best fitting line is the line that minimizes the square residuals. Okay? And the best fit line will always pass through the point x bar comma y bar. What is the point x bar comma y bar? Yeah, it's going to pass through the point that is the mean of x and the mean of y. So what is the point that has the mean of x and the mean of y? It's a data point. It's a data point. So, for example, if we were dealing with books and thicknesses of the book, okay, our data set, maybe we looked at 50 different books. X bar is the average number of pages across all 50 books. Y bar is the average thickness of those 50 books. Okay. If we were looking at this classroom of students, it looks that there's about 50 of you, okay? And we said, you know, what's your shoe size and what's your height, okay? If we might use the shoe size to make a prediction for how tall you are, okay? My x variable is what? So I'm going to use the shoe size to make a prediction for how tall you are. Which one's my x and which one's my y? Shoe size is x, and I'm using that to make a prediction for your height, y. Okay? Now, if we gathered the data across all of the students, x bar is the average shoe size. I don't know what that is. An 8. Okay? And y bar would be the average height, or that is 5'7". Okay? And the regression line will always pass through that data point. Okay? So whatever it is, if you figure out the mean of x and the mean of y, it's always going to go through that. Okay? Here, our slope, the slope, which is the letter b, is going to be equal to r times the standard deviation of y divided by the standard deviation of x. Okay? That's s sub y and s sub x. The standard deviation of y divided by the standard deviation of x. Do I need to write that, or is that okay?
What was that again? Can you say it one more time?
S sub y, this is the standard deviation of y. And S sub x is the standard deviation of x. What's R? The correlation. Okay, and we plug all those numbers in and we get B, which is the slope. And A is my intercept. And that's going to be equal to y bar minus B times x bar. Okay, and this ensures that it runs through the point x bar, y bar. Okay, so let's say we look at a whole bunch of people and we ask them let's say we ask them, how tall are you? So we asked for their height. Okay. And then we also asked, what is the inseam of your pants? Okay, so you buy jeans and you get about different pants inseams, right? Or is this only for men? Okay, so alright, so let's say we just looked at a bunch of men, okay, and we said, how tall are you? And what's your pants inseam, right? So we're going to have a positive trend, right? Because in general, people who are taller, they're going to wear longer pants, okay? People who are shorter, going to wear shorter pants. But you got some people with short legs and some people with long legs and things like that. But we're looking at height and pants inseam. Okay, so let's say the average height of all these men that we looked at is 70 inches, okay? We're using height to make a prediction about the inseam of their pants, okay? And let's say y bar, this would be what? This is the
Average of pants
the
inseam?
average pants inseam, right? This is the average height. And this is the average inseam length. Okay, so let's say the average inseam, I don't know, it's 31. Okay. Standard deviation of x, let's say, is 3. Standard deviation of y, let's say, is 1.7. Okay, this is the standard deviation of the heights. This is the standard deviation of their inseam lengths. And R is the correlation. Let's say between these two, the correlation is 0.85. Okay, so go ahead and use these things to figure out what our line of best fit is. Or do we not have for that? No, we do. Okay, so go ahead and take a minute. It should only take about that long to figure out the best fit line, or the equation of the best fit line. you guys are still working, or some of you are. Well, did anyone get this answer?
Yeah.
Yeah? Just don't be shy. Just raise your hand. Okay, you got it. You got it. Okay, three of you, four. Okay. Okay. Well, 4 is better than none. It shouldn't have taken so long. Okay. And maybe I didn't do a good explanation. I'm not sure. Okay. To get, this is the equation that we're going for, right? All right. What do we need to know? We need to know the intercept, and we need to know the slope. What's the equation for the intercept?
Y bar minus.
This is the equation for the intercept, right? A is equal to y bar minus b times x bar. Now what's the equation for the slope?
R.
B is equal to r times s sub y over s sub x. Okay? So I just need to plug numbers in to this thing to get my slope and my intercept. Okay? So let's try that out. So to calculate my intercept, it says I need to know y bar, b, and x bar. I don't know b, okay? So we're going to do this intercept second, and we're going to do the slope first. So let's find the slope. The slope is b, which is r times s sub y over s sub x. Okay? What is the value of r?
0.85.
0.85. What's the value of s sub y?
31. No, 1.5.
No, s sub y is 1.7.
Oh,
Okay.
that's where I messed up.
I have it right here.
Oh.
All right. And what's s sub x?
3.
3. Okay. So all I do is I punch this into my calculator, and what do I get? 0.4816666, right? So I'm just going to round this off to 0.4817. Now, you might have rounded off to a different value. It doesn't really matter, okay? So this is my b. Now, I'm going to use that to calculate the intercept. Okay, intercept is a equal to y bar minus b times x bar. What's y bar?
31.
Okay, 31. And what's b?
0.4817.
0.4817. And I multiply that by x bar, which is 70. Okay, and when I calculate that out, what do I get?
33.82.
Yeah, so I do 31 minus that, and I get negative 2.717 or something like that. 2.719 or something around there, okay? It's good enough. Yes, question?
A equals y minus bx. What formula is that?
That's this one?
Yeah.
Intercept.
That's the equation of the intercept. How to find our intercept. Alright, so I have my slope right here, I have my intercept right here, and I'm just using that to plug in to this. Y hat is equal to A plus BX. So I get Y hat is equal to negative 2.717 plus 0.4817. Is that okay?
Yeah.
Alright. Yes, we have a question.
Right over there where the slope is b equals r, is that a times, that little dot?
Yeah, that's a
Okay.
dot. That's a times.
You said that's a plus minus 2.717 plus?
Negative 2.717 plus
Oh, okay.
0.4817. Okay, because all I'm doing is that I'm plugging in the values I got for the intercept and slope into the equation
The x.
for a line.
Right.
Okay. Do I need to plug something in for x? Or y bar? No. Or y hat? No, this is the equation of a line. You've got an x and you've got a y hat. Okay, that's fine. Alright? You don't need to, it's fine that you have variables there. Okay? 'Cause it's a line. Alright, so, if someone says, okay, I'm 6 feet tall, what is the, what length pants do I wear? Okay? So, what do we predict? is the pant length of someone who is 6 feet tall. Alright? Okay, so let's just, 6 feet tall is 72 inches, okay? So what do we predict? How do we do this? We just plug in, this is our equation, right? Our prediction line, or our regression line. That says our prediction y hat is equal to negative 2.717 plus 0.4817 x. Okay, so I'm just going to plug in, what is my x here? 72. Okay. And I'm going to plug in 0.4817. And what do I get here? I get 31.9654. Okay? Practically 32 inches. Okay? So I say y hat, we can just say is 32 inches. This is the, I'm just rounding off here, okay? But that's basically what it's saying. So that says if somebody is 6 feet tall, 72 inches tall, what length do I predict their pants is? 32 inches, okay? Does that seem reasonable? I don't know. Is anybody here 6 feet tall? Willing to share your pants inseam? I don't know. No? Okay. Huh? Alright. It's not your waist size, it's your inseam, okay? 34? Okay, so maybe these equations aren't the best. But anyway, something around there, okay? So anyway, okay, so here's a good example. Okay, so let's say this is our equation, okay? And so let's say we found an actual person. The actual person says, I'm 6 feet tall, and the pants I wear, the inseam is 34 inches, okay? So actual data. The x is 72, and the y is 34, okay? What is the residual? Is my residual 2 or negative 2? Or 3? Or 4? What is it? So the residual is the actual minus what I predicted, right? So here, the actual data point was 34. What we predicted for somebody who has 72 inches tall, we predicted this to be 32 inches. So the residual here is 2 inches. Okay, so that means the actual length is 2 inches longer than what I predicted. Okay.
I have a question, sorry.
Yeah.
I don't know if I missed this, but is that always on a plus, that equation right there, or no? The a plus bx?
It's always a plus bx.
Okay.
But b can be negative. Okay? One would be negative.
So it's okay. So it's always a plus.
One would be negative though. It's another question. Wasn't you guys?
Negative relationship.
Yeah, if the relationship is negative, if my correlation is negative, okay? Because the standard deviations are always positive, right? Because it's the square root. After you square everything and you add them up, you're never going to get a negative when you take the square root of something. Okay? So this part will always be positive, but the correlation could be positive or negative. So my slope can be positive or negative. So I could have a negative slope, and there would be y hat plus is equal to a plus bx, but my b is negative. Okay? Alright, what was my slope here?
Point
0.4817. Okay, so the slope is 0.4817. What is the interpretation of the slope? What does it mean that my slope is 0.4817?
Slightly positive.
Okay, well, does this tell us anything about the strength of the relationship? No, the slope doesn't tell us anything about the strength of a relationship. Where do we find out the strength of a relationship?
R.
In R. R is what? 0.85. So that means it's pretty strong. It's a pretty strong relationship because it's a lot closer to 1 than it is to 0. So R is pretty strong. So the slope doesn't tell us anything about the strength of a relationship. Okay? What it does tell us is it tells us about our predictions. Okay? And it says that if x goes up by 1, how much is y going to change? By 0.4817. Okay? So if I increase x by 1, my prediction for y, my y hat, increases by 0.4817. So in the context of this example, what does it mean to increase x by 1? What does it mean to increase x by 1 in this example? Yeah, it means if we pick a different person who's 1 inch taller, okay? So here is the interpretation of the slope is if we increase x by 1, okay, we predict, our prediction for y to increase by the slope, okay? For this example, it's if we find another person who is 1 inch taller, okay, because that's how my x is measured, right? Then what happens? If we find a person who's 1 inch taller, our prediction for the inseam, it doesn't mean the inseam actually changes by this much, but it means our prediction for the inseam goes up 0.4817. Okay, it means practically half an inch. Okay, if we're comparing another person who's 1 inch taller, we predict the pants that they wear, the inseam, is half an inch longer. Okay, is that okay?
Yeah.
And so you're going to have different examples where the situation is different, and I need you guys to be able to figure out what the slope means as it relates to the problem. Okay. The intercept, what was the value of my intercept? Negative 2.717. Okay. What is the interpretation of the intercept? Okay. The intercept is our prediction for y if I plugged in 0 for x. Okay. Now, in this situation, there's no practical interpretation, because what does it mean to have an x of 0? It means the person has 0 inches tall, so this person doesn't exist, okay? But it would be if there were a person who's 0 inches tall, then I would predict their inseam to be negative 2.7 inches, okay? That doesn't make any sense, because there's no practical interpretation. But sometimes it makes sense to plug in a 0 for x, and then the intercept is your prediction for when you plug in x for 0. Okay, plug in 0 for x. I know we're almost out of time here, so just in these last couple of minutes, okay, I just have a few warnings about regression, okay, and you're gonna have some homework problems to do. The thing about regression is that regression is heavily influenced by outliers, okay, so and the other part is that do not use regression to make predictions outside of your data range. Outside of the range where you collected data. Okay, so don't. Sometimes when we make regression lines, we want to predict the future. We say, okay, every year this number has gone up. So 10 years from now, we predict this to happen. You cannot use regression for that because we don't know what the future looks like. Okay? So here's a silly example. If let's say a parent has a child, okay, and the child is walking and they're measuring how tall this kid is, okay, and every year the kid gets a little bit taller, and they create a regression line, okay, and at 10 years old the kid is let's say 5 feet tall, okay, and they say, oh, wow, this kid's tall, and at this rate, by the time he is 20 years old, he's going to be 9 feet tall, okay? Now that would be silly, okay? Because what we know is that at a certain age, people stop growing, okay? And so we can't do stuff like that, okay? So do your homework and do the regression stuff. Please make sure you really understand the topics and do your reading.